Hey Data Junkies, welcome back. We're moving right along with the analysis of variance, or ANOVA, one-way ANOVA to be specific, and you've just had your foundations put forward and you've seen the F ratio, the math that starts to go into it. So let's go ahead and move this video along to start showing you how you can calculate one of these one-way ANOVAs by hand using the formula that was given to you before. Now with this particular example here, we're going to be using a nice little treat example with the Munchkins and the Wicked Witch, and I'm just going to give a little shout out credit to our Stats Institute. There's a link down here in the slides that takes you to their YouTube video. This is actually, I don't know if they're the ones that created it, but I was inspired to use this example from them, and I use it in a slightly different way with the math, and they approach it, but we get to the same answers and the same conclusions. But I definitely suggest check them out and give them a good look. It's a great site to learn more statistics. So the idea behind this particular example here is that following a series of complaints about the Wicked Witches, that the Wizard of Oz conducts a survey to determine if certain regions of Oz have more problems than Wicked Witches than other regions. He randomly surveys 5 Munchkins from each of the 4 regions and records the number of complaints he has received about the Wicked Witches' wicked witchedness from each of these Munchkins. And so we're asking ourselves, is there a difference in which wickedness between the regions? So in order to do this, we'd have to collect some of our data here, and I have it tabulated out. And we're wondering, do these Wicked Witches vary by region? So we have our 4 regions, north, south, east, and west. And then we have the number of complaints, where each of those numbers represents a Munchkin who has been surveyed and reported, and that number is the number of complaints reported by that particular Munchkin. And then the means, that is the mean within that particular group. So the first mean of 1 is the average number of complaints for the north, 1.4 is the average number of complaints for the south, and so on. N is the total number of Munchkins in our survey, so we have 20 of them, 5 in each region. 4 is the number of regions that we have, and then we have what's called the grand mean. So we can calculate the grand mean in one of 2 ways. I can either take all of those complaints of the 20 Munchkins, add them together and divide by 20 in order to get the mean of all of the complaints, or I can take the 4 different means for each group, add them together and divide by 4 for the total number of means, and I'll be getting the mean of means, which is why we refer to this as the grand mean of the entire data. These are going to become the data points that we're going to use to calculate out the one-way ANOVA. Everything that we need is right here. So just to go ahead and recap with this one-way ANOVA process, we're going to ask ourselves, do we have the appropriate statistic? Well, we have 4 independent groups and an independent ratio dependent variable, so check. So far on study design, we're good for one-way ANOVA. We're going to state the null and alternative hypothesis. The alternative is that all of the means are equal, so that's going to say that the average number of complaints in the north is equal to the average number of complaints in the south, and to the east and to the west, respectively, an average number of complaints per region. And the alternative is going to say at least one of these is different. We don't know which region, but at least one of them is different. Then we go ahead and select a level of significance. I'm going to go ahead and choose an alpha at 0.05. I could maybe even go higher at 0.1 because of a rather small sample size here, but I'm going to be comfortable with 0.05. Then we're going to go ahead and calculate the F statistic, and we're going to make a decision based on the results that we get. Now, I'm going to reintroduce you to the ANOVA math machine here. This is the formula that was in the foundations lecture and all of the different parts to it. We're going to start unpacking this piece by piece. Now, again, here are the different parts of it as well that we're going to start using to calculate out the one-way ANOVA, and I'm going to take bits and pieces of this one at a time for us to work on. So first we're going to start with what's called the total sum of squares. The total sum of squares is talking about how much variation is there within all of the regions, and between, within, everything going on. How much differentiation is there going on in here? So what I have charted out are the 4 regions and columns across the top, and then the Munchkins are going down in the columns with their numbers being represented. So this is our starting raw data here. Then what I can go ahead and do is start calculating what we call the total sum of squares. And so in order to make this work, each cell in here is going to get subtracted from the grand mean, which was 2.55 on the previous slide. So the very first Munchkin up in the north is at no complaints at 0, is going to get subtracted from 2.55. And the next one down below at 1 complaint is going to get subtracted by 2.55. And so on. Every observation in here is going to get subtracted from the grand mean. And then after it has its subtraction, we're going to square it. This is where we get into the term the total sums of squares. So subtract from the grand mean, square it, and then we have all of these squared values in our little table here. So the very first Munchkin that had 0 complaints has a square value of 6.5. Remember, these are all positive because they're squared. And then we're going to go ahead and add them all up. And we add up the entire table. We add it up to about 59.95. Or 59, rounded to 60 if you want. And that's where we come up to. Now the next, we're going to take that sum of squares total. We're going to put it away for now. We're going to come back to it later. Then we're going to look for the sum of square between. The sum of squares between, it's a very easy step to do, but it can be a very lengthy step, especially if you have a lot of groups. It's a lot of small basic math that gets chained along together. And that chaining effect is for the very first cell that you're going to get, you're going to take the number, the sample size of that group, not of everybody, not all 20 Munchkins, but in this case 5, because 5 is the number of Munchkins in each group. And this is going to be the number of that particular group, so n sub k, multiplied by x bar sub k minus x bar. What that means is the average of a particular group minus the grand mean. That gets squared, then multiplied by n sub k. And we're going to repeat this for each particular group. We have 4 groups, so we're going to have 4 of these chained together. So we're going to start with the the number of Munchkins in the north times 1, which is the average number of complaints in the north, minus 2.55. That difference is squared, multiplied by 5. And I'm going to carry along to the next part, where I have 1.4. That was the average number of complaints for the south. Gets minus from the grand mean of 2.55. Gets squared, multiplied by 5, which is the number of Munchkins in the south. Then we go to 3.33, which is the average number of complaints in the east. That gets subtracted from the grand mean of 2.55, squared, multiplied by the number of Munchkins in the east of 5. Chain that to the last one, where we have the number of complaints in the west, 4.2, subtracted by the grand mean of 2.55. We square it, multiply it by 5, which is the number of Munchkins out in the west. We add all these up, and then we get the sum of squares between is 37.75. So far, so good. Once we have sum of squares total and sum of squares between, it's a simple subtraction process in order to get sum of squares within. Within and between, as long as you have 2 of these 3, you can always go ahead and get the third. Between and within get added to give you total. Total minus between gives you within. Total minus within gives you between. So there's just an additive and subtractive process there. So once we have these 3 pieces of information, we can go ahead and start calculating degrees of freedom. Previously I said degrees of freedom between is measured by k minus 1. K is the number of groups. We had 4 regions, so 4 minus 1 we have 3. 3 is our degree of freedom between. Then we have degrees of freedom within. That's n minus k. N minus k, n is the total number of Munchkins all together in the survey, minus k, the number of groups, which there are 4 regions, so that's 20 minus 4 is 16. I gave you an alternative approach you could use. That one's also going to give you 16, so use whichever one makes you more comfortable. I happen to like this particular approach. So once we have the degrees of freedom between and within, and we have the sums of squares between and within, then we can go ahead and start calculating the mean sums of squares between and within. And from there, it's simple division. You take the degree of freedom within, divide it into the sum of squares within. That gives you the mean sums within. Then we're going to go ahead and take the the degrees of freedom between, divide it into the sum of squares between, and that's going to give you the mean sums of squares between. Simple divisions. Once you have mean sum between, mean sum within, then you can go ahead and get the F ratio. And that's just within divided in between, MSW divides into MSB. That gives you your F ratio. And what we have here, when this worked out, was the mean squares between was 3, divided into the sum of squares between of 37.75, gives us the mean sums of squares of 12.58. Then we do the withins. There were 16 degrees of freedom there, divided into its sum of squares of 19.2, gives us an MSW of 1.0. You divide 1.0 into 12.58, that gives us our F ratio of 10.4861, or as we just want to round it to say 10.5. That would be fine. So the F ratio of this particular analysis is 10.5. Then we need to get a critical value, so you turn to the F critical value table. I give you two that you can choose from. This is the one that has more alphas to choose from. The other one just has 0.05 and 0.1. So in this particular case, you look for the degree of freedom from the numerator. That was our 3. That's going to be in the columns. Then you move to the rows. Go down to the degree of freedom from the denominator. That was 16. From inside there, find which level of alpha you're using. We're using 0.05. Cross-reference that with the column, and we're going to find a critical value of 3.24. So we then ask ourselves, is our F statistic obtained of 10.49 larger than our critical value of 3.24? Absolutely. And so we are statistically significant. And we can go ahead and report this using APA format of F in parentheses 3, 16 equals 10.49 for our two digits after the decimal. And then I'm just using a p is less than alpha 0.05, and we're fine. In this case, the p-value was too small to write at 0.0047. I chose to use just the 0.05 for convenience and to keep it looking clean. Now, just to keep in mind here that this is great. We did this by hand, and we're going to do this in Excel for another video. But there's some other little problems we run into, like some of the assumptions we need to check that makes it difficult to do by hand. So in future videos, we're going to break apart some of the assumptions that we need to know about the one-way analysis of variance, the one-way ANOVA. And with that, I'll see you all next time.